Okay, we are in Unit 1. Still, we are in Chapter 5, spiraling back through. We are left off going over the empirical rule and seeing how it can be a useful tool even if it's not exact answers that we get. It's useful because it can help us quickly estimate the percentages to see how far off we might be with some of the approximations and things that we do make. Okay? So I left off with this example saying if the range of a bell-shaped data set is 60, that's our range, which means low to high. What is an estimate for the standard deviation, right? So from low to high, it says the data set is 60. Using the empirical rule, right, almost all data, all right, almost all is between those 6 standard deviations, right? So a quick estimate would say, okay, well, if almost all of it's between 6 standard deviations, and I sit there and say, you know what, if the range is 60, then if I divide that by 6, I get 10. And using the empirical rule of 95% of all data is between 4 standard total deviations, then I can take it and say that. So my point is I'm narrowing down what I think each standard deviation with a rough estimate should be around, if that makes sense. Worst case scenario, right? Best case scenario in between there. That's what I'm saying. This helps us determine where the standard deviation should be between. So I can already tell you that my standard deviation, this is like a worst and best case scenario. It's probably between 10 and 15. Now I know it's still a broad range, but I can at least find a pretty good idea of what my standard deviation should be. And this helps us determine that. So the standard deviation is between there, and thus if the standard deviation is said to be 0.32, I know that I did something wrong, right? It's definitely not right. Or the standard deviation is said to be like 87. It's like, yeah, no, I did something wrong. So I'm giving you keys to figure out what might be wrong. A reasonable standard deviation would be like 12 or 13, for example. This is not an accurate tool. It's just a rough estimate, that's all. It helps point out and narrow down our standard deviation. That's all. All right, so hooking back up with histograms again and some more measures of central tendency. Suppose we have a detailed histogram, right? But I don't know. Now, if I was to scan this right now, it's kind of looking like this. It doesn't look normal. It kind of looks more skewed to the left right now. Just like a rough guess. I don't have any numbers, right? Our measure of central tendencies fit naturally into this. All right, I'm trying to show you how this stuff works. The median is like the middle. Like if you were to look at this data set, I don't know how high they are, but if I was to like draw a line right there and say that that's a spot, that's a spot, that one, like if I keep drawing these lines to roughly figure it out, right? And I count them up. Like this is about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45. It's looking at like 45, right? Well, the median is the middle. That's 45 like blocks that I cut it into. I'm looking for around 22-ish, 23-ish. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. It's somewhere around in here is the middle, right? And notice that's where we have the line. It's somewhere around in there is roughly the middle. That's roughly where it's at. So this is kind of accurate with it, right? Logically trying to calculate and figure out where the middle of my data should be. Okay? The median divides a distribution into half, right? About 50% of the data is here, about 50% is here. So it represents by a line that divides the area of that histogram in half, right? The mean is affected by the spacing of all values. All right, the mean. That is me averaging everything together. Some are higher than others, some are lower. I have more here than, more here than down there, averaging it all together, right? It's affected by the spacing of those values. How far out? That's what we talked about outliers before with means. Like it really does affect it. All right, I don't seem to have a ton this way. I have more data, all right, over here than out here. That is what it's shaping like. And therefore, if the histogram is a solid region, the mean corresponds to a line passing through the center of gravity, or balance. The mean distribution spread thinly far to the low side is said to be skewed left, which is what we know in picture, right? It looks skewed left. I said that before. On data skewed left, the mean is normally less than the median, all right? On data skewed right, the median is normally less. Basically what we're saying is, when it's skewed one direction, let me go back to a picture here. If it's skewed this way, the mean's getting pulled down that way, because that one outlier or whatever that might be down there is pulling that average down farther. If it's skewed to the right, then the mean should be more this way. So if it is normal right down the middle, then that normal curve has the mean right in the middle, is basically what they're trying to get at with this. So they said, if the data is skewed right, then the mean is more down there, and the median is normally less than that. All right. So take a look at an example. Suppose that the faculty salaries at a college have a median of $82,500 and a mean of $88,700. So you're trying to guess about the data, right? Do you think it's normal? Do you think it's skewed? How do you think it is? So, with the mean higher, which means this way, I'm going to guess, just by seeing that maybe it's skewed a little to the right with the median lower. That would be my guess. Now, I could be wrong, but the shape, that's what I'm implying. If they're close to one another, it's probably pretty normal then, right? What does this indicate about the shape of the distribution? So, well, since the median is less than the mean, the salaries are probably skewed. Again, it's hard the way the books write it like that sometimes. Again, if the data set is skewed right towards the higher end, that means there's outliers more towards the right, which means the mean's getting pulled that way. That's why it is skewed to the right. That means there are probably a few lightly paid professors, highly paid, with the bulk of the faculty at the lower end, more than likely. This idea is helpful and can be useful, but it's not a hard, fast rule, so I need you to keep that in mind when we're doing this. It's a good rule. It helps, but it's not the end-all, be-all is what we're saying. So, look at this example. It looks skewed to the right. If I was to guess, I'm probably thinking that my average is probably somewhere around in here, and my middle is probably somewhere over in here, right? The median, which is 3, is greater than its mean, which is 2.97. How did the data skew? All right, so taking a look there. It looks skewed to the right. I can just look at it from that standpoint and see. But even here, the median is 3, but the mean is 2.97, which means it's kind of like right over here. So this is just an example showing you that I can't always just assume that by looking at it. But technically, I don't have too many outliers here either. It isn't like I have a 10 or a 12 or a 15 way out here, right? We have seen that relative frequencies are represented by relative areas. Basically, they're like the same thing. You can count up the areas to get the idea and get those percentages. And so labeling the vertical axis is not entirely crucial. All right, it's helpful, but it's not crucial. And that is one of those things that you need to keep in mind, because that question pops up on AP tests numerous times. It's not crucial to label that vertical axis. If we know the standard deviation, the horizontal axis can be labeled in terms of z-scores then, okay? If we know it. In fact, if we are given the percentile rankings of various z-scores, we can construct a histogram. So for example, so you can see what I mean. Suppose we are asked to construct a histogram from this data. All I know is the z-scores and a percentile ranking. That's all that I know. All right? Excuse me. We note that the entire area is less than z-score of 2 and greater than a negative 2, which means there's nothing out here. All right? And there's nothing out here. It's actually everything is in between 95%. of all data is supposed to be there. So that's where it's at. Also, 20% of the area is between z-scores of -2 and 1, right? 20% of the data is there. 40%, 10%, 30%, right? We can see the layout, the percentage of the data, where it's located between what and what. 10% of the data is located between there, 30% of the data there. Thus, the histogram, like if I was to roughly do it, I cut this into, it's 100%, right? So I just cut it into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We said 20%, 40%. Like, there you go. There's roughly my histogram. I didn't need the vertical axis at all to calculate this, to figure it out. Or, I don't even need those lines anymore. Those lines help me to make it, but there is roughly my histogram made for it. And I don't even know what that vertical axis is. Take a look at this example. Suppose we are given 4 in-between z-scores as well. So, if I'm given even more z-scores the whole way down, and now I'm given even more detail, I can make my graph even better, right? So when we go to label it, basically there's -1.5, right? Well, between -1.5 and -2 is about 5%, right? So what we're saying is these are now 5%, and that's probably another 5%, like height, and that's another 5%, and 5%. So I probably just chop them up into about 5 percentages instead of 10 percentage points. So instead of there being 20 blocks, 10 blocks, there's probably like 20 little blocks there to count up to figure it all out. If we had 1,000 z-scores, perhaps the histogram could even look like that, which is where dot plots end up coming from indirectly. Right, trying to figure out the thousands of each spot in between there, and the height at many points, right? It says the height at any point is kinda meaningless. You got an idea of the shape, but it's not telling me as much of a detail. So what's important is relative areas. For example, if the final diagram, in that last diagram, what percentage of the area is between z-scores 1 and 2? It's still 30%. Even though you look at this one, you go, between what? What do they say again? Between 1 and 2. Between 1 and 2. It looks like maybe there could be more. It's still the same percentage. Nothing changed. I have just more spots where I'm calculating percents, but it's the same overall. It's still 30%. That doesn't change, right? It's still between 1 and 2, it was still 30%. Even if I calculated 1,000 different z-scores, it's still the same. What percent is to the left of 0? -2 to 0. So -2 to 0 is 60%. That doesn't change either. More z-scores don't change the overall percentage. They might change the shape of the graph, but they're not going to change what percentages are still in between there. So when I come back here, we will hit on some more with some box plots.